Cocooned in a fragile shell of atmosphere, planet Earth rotates serenely on its axis like a blue and white jewel. Home to as many as 100 million different species and the cradle of humanity, our unique planet is dominated by the oceans from which life first emerged. Arthur C. Clarke said we should have called the planet Ocean rather than Earth. And from space, it is easy to see why. Our journey begins with the smallest step of all. And already the Earth is a distant presence. Moving at the speed of light, which travels 186,000 miles a second, we would reach our nearest neighbor in a mere 1.3 seconds. The Moon is huge for a satellite, and at a quarter the size of Earth, compared to its parent planet, it is the largest satellite in the solar system. Ahead of us lie the other terrestrial worlds of the inner solar system, formed over 4 billion years ago from rocky debris orbiting the newly born Sun. Beyond them, we will visit the giants of the outer solar system with their fleets of accompanying moons, before plunging into interstellar space and embarking on the longest voyage of all, a journey that will take us back to the dawn of time and the Big Bang itself, across 13.4 billion light-years. Beyond the asteroid belt lies the realm of the giants. 4 gargantuan worlds composed of gas or ice inhabit the outer solar system, all dwarfing the Earth and the rocky inner planets. Mighty Jupiter is the first of the outer worlds, a planet so vast its mass and volume are greater than all the other planets combined. It has often been described as a failed star. Like the Sun, Jupiter is predominantly made up of hydrogen, but it would need to be 80 times more massive to begin the hydrogen fusion process that powers the stars. The second largest planet in the solar system, Saturn is also the most insubstantial. It is the only planet less dense than water. In the unlikely event of a large enough ocean being found, Saturn would float in it. The tiny moon of Enceladus is one of the solar system's most intriguing worlds. Trapped in a gravitational tug-of-war between Saturn and several of the larger outer satellites, Enceladus is pulled this way and that. As the moon's shape is distorted, heat is generated, melting ice and giving rise to liquid water running just a few meters beneath the surface. Cracks in the ice allow plumes of material to boil into space, settling back on the surface as light snow. With water so close to the surface, could Enceladus play host to primitive life? Voyager 1 is the most distant man-made object in the universe. Poised to depart our solar system, it must first pass through the Oort cloud, a vast swarm of icy debris orbiting at the furthest reaches of the Sun's influence. Beyond the solar system, light hours will become light years as we span the enormous distances between the stars. Our galaxy contains 100 billion stars clustered together in a flattened spiral disk 100,000 light-years across. Within the galaxy, stars of near infinite variety, from slow-burning red dwarfs to massive blue hypergiants, are born, flourish, and die in a near-endless cycle. Star birth and star death present us with perhaps the most spectacular images in the cosmos. Star birth begins in stellar nurseries like the Eagle Nebula. Spanning 20 light-years, these vast clouds of dust and gas are the seeds of future stars. Where the dust clouds begin to coalesce, a protostar may form, which, as it increases in size, draws ever more material into its gravitational embrace. When it becomes massive enough to fuse hydrogen atoms within its core, a new star is created. The light of these newborn stars illuminates the clouds that birthed them. To witness the spectacular events of star death, we must first head closer to home. Mid-sized yellow dwarf stars like our own Sun are common throughout the galaxy, and their lives can be counted in billions of years. But in another 5 billion years or so, our Sun will finally exhaust its store of hydrogen and helium. With these elements depleted, the furnace at the heart of our Sun will no longer be capable of nuclear fusion. Instead, fusion will switch to the outer layers, causing its outer shell to expand as it transforms into a red giant. Then, in the throes of death, it will cast off its outer mantles in a final flowering of fluorescing gas to become a planetary nebula. Lasting no more than 50,000 years, planetary nebulae are short-lived phenomena and come in a near-infinite variety of strange and beautiful forms. At the center of every planetary nebula, a stellar ember is left behind, a small, slowly cooling core the size of a rocky planet known as a white dwarf. At the heart of the Red Spider Nebula, the hottest white dwarf ever observed burns at 500,000 degrees Celsius, driving waves of gas before it on a scalding stellar wind. While the majority of stars end their lives as planetary nebulae, the true giants of the galaxy face a different, even more spectacular fate. Spanning some 50 light-years, the Carina Nebula is a massive cauldron of star formation, and its hydrogen-rich clouds have birthed one of the largest stars known, Eta Carinae, 100 times more massive than the Sun and 4 million times brighter. Supergiants like these burn their fuel so fast that their lives span just a few million years, and time for Eta Carinae is almost up. Like their smaller stellar cousins, supergiants fuse hydrogen nuclei into helium and helium to carbon. But where lesser stars are unable to fuse carbon, the crushing pressure at the heart of a supergiant transmutes carbon into oxygen, then oxygen into silicon, and finally silicon into iron. But an iron heart is a death sentence, for not even a stellar alchemist can transmute iron. As the inert iron core builds, so the star abandons itself to gravity. Within 1/10 of a second, the star's iron core, a sphere the size of our Sun, collapses into a city-sized neutron star. The star's collapse triggers an explosion so great that the resulting supernova can briefly outshine the entire host galaxy. If Eta Carinae were observed to explode from the Earth, it would be so bright that you would see it during the day, and you could even read a book by its light at night. The Crab Nebula is all that remains of the supernova that lit up Earth's skies in 1054 AD. At the center of this nebula lies the Crab pulsar, a neutron star only 25 kilometers in diameter. The Crab pulsar's energy output is 750,000 times greater than our Sun's and illuminates the entire debris cloud that extends for 10 light-years around it. When the biggest stars of all go supernova, what's left behind is the most exotic of stellar phenomena, a black hole. Enigmatic, destructive, and so dense that even light cannot escape their grasp, black holes can never be directly observed, but they can be detected by the mayhem they wreak on their local environment. At the heart of our galaxy, where the star fields are thickest, lurks the black hole Sagittarius A star. Weighing in at 3 million solar masses, the entire galaxy revolves around this supermassive dark entity. While it currently lies dormant, in the deep past, this huge black hole fed voraciously on stars and gas in the heart of the galaxy, and in the far future, it is sure to reawaken. Up until the early 20th century, most astronomers thought the Milky Way was the universe. It took the calculations of Edwin Hubble in 1924 to prove otherwise, and today we know the Milky Way is just one of at least 100 billion galaxies. The Milky Way has the close company of several dozen other galaxies. Together, they form the Local Group, a collection of galaxies occupying a sphere 10 million light-years across. About a third of the galaxies we see in the local universe are spirals. The magnificent spiral arms of the whirlpool are factories of stellar construction. Dark clouds of gas are compressed into bright pink star-forming regions. But such grand-scale creation is born of cosmic violence. The whirlpool is busy dismembering its dwarf companion, which feeds the intense wave of star birth. The sight of galaxies tearing each other apart, or larger specimens consuming smaller satellites, is commonplace throughout the cosmos, as gravity forces traveling companions together. Our own Milky Way is on a collision course with our neighbor, Andromeda. In 3 billion years, the two giants of the Local Group will meet head-on. When a collision between spiral galaxies occurs, the result can lead to the formation of a giant elliptical galaxy. About 60% of all galaxies are elliptical and range in size from paltry loose clusters of stars to giant spheres containing 1 trillion or more stars. During a galactic collision, the dust and gas that allows spiral galaxies to regenerate their star population is either completely used up in a final burst of star formation or blown into deep space and lost forever. Shorn of their regenerative capacity, ellipticals are filled with aging, dimmer stars. It is the final destiny of all galaxies to merge with their neighbors and become elliptical. We have now traveled a colossal 420 million light years, but in cosmic terms, we are still in our own backyard. Comparatively, intergalactic space is more densely populated with galaxies than interstellar space is with stars. From here, we begin to see the large-scale structure of our universe. As we have seen from galactic collisions, galaxies don't live isolated lives. They flock together, forming clusters, then superclusters, dense metropolises so massive they can visibly warp space. On this scale, galaxies cluster like grains of dust to a celestial veil of cobwebs as they form vast interconnected filaments and sheets of matter threaded around central voids. As we race through the filaments, we travel ever further back in time. The light from these distant galaxies takes billions of years to reach us, so effectively we are looking billions of light years into the past. This tangled maze of filaments can lead us 13.4 billion light years from Earth, 13.4 billion years into the past, to a time when the very universe was a mere 379,000 years old. This is the event horizon that conceals the mysteries of the universe's birth. Beyond its horizon, a wall of superheated plasma impedes light's progress, and our journey can go no further. For what stands before us is the Big Bang itself.